0.5% error on your Mars orbital insertion burn puts you 800 kilometers off target and into a solar orbit you'll never escape. 3 seconds too short on a 10-minute deceleration, and physics writes your obituary before you even realize the burn failed. You're staring at Mars through the cupola, Olympus Mons breaking the horizon, Valles Marineris cutting across the rust-colored terrain like a scar. 7 months of transit, 225 million kilometers of perfect navigation. The relief floods your chest. You made it. Then the navigation console chimes, not an alarm, just a polite notification tone. Trajectory deviation detected. The flight engineer's voice cuts through. We're hyperbolic. Burn terminated 3 seconds early. We're not capturing. You don't understand the words at first. Mars fills the viewport. The planet is right there. How do you miss something you can see? Orbital insertion at Mars requires slowing from 5.5 kilometers per second down to 3.4 kilometers per second, a velocity change of 2,100 meters per second. Your main engine fired for 10 minutes. It was supposed to fire for 10 minutes and 3 seconds. 0.5% short. 0.5%. The kind of error that gets rounded away in engineering reports, the kind of tolerance that passes quality control reviews. In orbital mechanics, 0.5% is the difference between a stable orbit and a death sentence. The math is simple, brutal, unavoidable. Your velocity is now 3,425 meters per second instead of 3,400 meters per second. 25 meters per second too fast. Doesn't sound like much. You could sprint that speed if you had 20 seconds, but you're not sprinting. You're falling past a planet at interplanetary velocities, and Mars gravity is bending your trajectory into a hyperbola instead of an ellipse. The navigation computer updates in real time. Periapsis altitude, 380 kilometers. Approach velocity relative to Mars, still decelerating but not enough. The planet's gravitational field is a funnel. You needed to slow down hard enough to get caught in the funnel's bottom. Instead, you're sliding along the curved sides, picking up angular momentum, being flung back out into space. Your trajectory curves around Mars. The planet's gravity accelerates you as you fall toward periapsis, closest approach. For 17 minutes, you're technically in Mars' sphere of influence. The crew watches the altimeter count down. 300 kilometers, 200, 150. This is as close as you'll ever get. Then the numbers start climbing again. 200 kilometers, 300, 500. The planet is pushing you away now, converting gravitational potential energy back into kinetic energy. You're accelerating. By the time you cross back out of Mars orbit space, you're traveling at 5.1 kilometers per second relative to the Sun, faster than you arrived. Mars used you as a gravitational slingshot and flung you into an elliptical solar orbit with an aphelion somewhere past Earth and a perihelion that'll take you uncomfortably close to the inner solar system. The crew engineer pulls up the fuel reserves. You've got 220 meters per second of delta V remaining in the tanks. Enough for minor trajectory corrections. Enough to dock with a station or adjust your parking orbit. You need 2,000 meters per second to cancel your hyperbolic excess velocity and recircularize back to Mars. The deficit is 1,780 meters per second. You're short by a factor of 9. The computer runs the calculation anyway because computers don't understand futility. Course correction to Mars capture orbit, insufficient propellant, mission abort recommended. Mars is shrinking in the viewport now. You can still see Olympus Mons, the volcano that's 3 times the height of Everest, reduced to a bump on a sphere that's getting smaller. In 6 hours, Mars will look like a bright red star. In 3 days, you won't be able to distinguish it from the background stars without a telescope. Your new orbit takes 520 days, longer than it took to get here. Your life support consumables were budgeted for 240 days, 7 months to Mars, 30 days in orbit, 7 months back to Earth, plus 30 days contingency margin. You're now on a trajectory that won't bring you anywhere near Earth for 520 days. The oxygen will run out in 190 days. CO2 scrubbers will saturate in 210 days if you stretch them. Water recycling will fail before that. The math doesn't close. The crew knows it. The computer knows it. Physics knew it the moment the engine cut off 3 seconds early.
The failure investigation will happen later. Maybe a sensor miscalibration. Maybe a fuel flow regulator stuck partially closed. Maybe a software timing error in the burn sequencer. Doesn't matter now. What matters is that orbital insertion burns don't have a retry button. You get one chance because the fuel budget doesn't allow for mistakes. Conservative mission design allocates 400 meters per second of reserve delta V specifically for this scenario, enough to enter an elongated elliptical capture orbit if the primary burn fails, then attempt a second insertion 3 days later after correcting the problem. Your mission planners went with 220 meters per second reserve because the mass savings allowed an extra ton of cargo. That extra ton of scientific equipment is going to orbit the sun forever alongside your desiccated corpses. The crew is silent. The pilot brings up the solar orbit projection on the main display. The trajectory loops out past Mars, swings back toward Earth's orbit, but Earth won't be there when you arrive. The planet will be 60 million kilometers away on the other side of the sun. Your orbit crosses Earth's orbital path, but Earth isn't an orbit, it's a moving target, and you're not going to hit a moving target when you're dead. The trajectory continues, around the sun, back out toward Mars's orbit. Mars won't be there either. The orbit is stable. Your spacecraft will circle the sun for millions of years, a monument to 0.5%. Someone suggests using the Mars atmospheric drag to slow down. Circle back, dip into the upper atmosphere, aerobrake until you bleed off enough velocity to capture. The engineer pulls up the numbers. Your periapsis was 380 kilometers. Mars' atmosphere at that altitude has a density of effectively 0. You'd need to descend to 120 kilometers to get meaningful drag. Your spacecraft isn't rated for atmospheric entry. The solar panels would shear off, the hull would overheat. Even if you survived, you'd need dozens of passes to bleed off 25 meters per second of excess velocity, and you don't have the fuel to lower your periapsis to 120 kilometers anyway. That maneuver requires 180 meters per second of delta V. You have 220 total, and you'll need that to orient the spacecraft for communications, to maintain attitude control, to keep the solar panels pointed at the sun for power. You can die with the lights on or die in the dark. Those are the options.
The communication officer opens a channel to Earth. Light speed lag is 12 minutes. The message will take 12 minutes to reach Earth. The response will take 12 minutes to return. 24 minutes round trip. Mission Control, this is Mars Transit Vehicle Ares 7. We have failed orbital insertion. Hyperbolic trajectory confirmed. Insufficient fuel for recapture. Request immediate abort options. The words sound calm, professional. The voice doesn't shake. Training holds. The message transmits. Then there's nothing to do but wait. Everyone knows what the response will be. There are no abort options. There's no rescue mission. There's no second chance. You brought everything you needed to survive, and it's not enough. Because you needed to be in Mars orbit, and you're not in Mars orbit. Somewhere in the computer logs is a timestamp. 8:47:23 mission elapsed time. The moment the engine shut down. 3 seconds early. 0.5% short. The moment everyone aboard died, even though their hearts are still beating, and their lungs are still breathing, and Mars is still visible in the viewport, a red disk against black space, shrinking.